So let us start with today's session. So yesterday we discussed the background of CPU scheduling and different criteria using which we want to assess different algorithms. And 5 criteria we discussed. One is CPU utilization, then throughput, turnaround time, waiting time, and response time. Where first 2 parameters, CPU utilization and throughput, we expect it as a max, whereas turnaround time, waiting time, and response time, they should be less, right? So, can you see the presentation? Somebody please respond on chat. Hello, am I audible?
Yes, sir.
Okay, fine. So, let us start with the first algorithm of CPU scheduling, and it is first come, first serve, FCFS scheduling. As the name suggests, first come, first serve, whichever process appears first will be scheduled first. So this is the simplest one where, like for example, on the slide you can right now see there are 3 processes, and these 3 processes are process P1, process P2, and process P3. So 3 processes are there, and the CPU burst time is given there. You simply call it as a burst time. Actually, burst time is there for CPU also and for IO also, but if it is just mentioned like burst time, you treat that as a CPU burst time. So this should be CPU burst time. Meaning of this is, say, some sort of 24 units of time. I'm saying units because it could be anything like milliseconds also. Okay. So meaning of this is like P1 needs 24 units or unit times of CPU. P2 needs 3 unit time of CPU, and P3 needs 3 unit time of CPU. So that is what its meaning is. So P1's bus time is 24, P2's bus time is 3, and P3's bus time is again 3. And then now suppose the processes arrive in the order P1, then P2, and then P3. That means first upon P1 arrives into the system, then P2, and then P3. So according to first come and first serve scheduling, what happens is first upon P1 will be scheduled. Once that is finished, now this part is very, very important. Once P1 is finished, then P2 is scheduled, then P3 is scheduled. Meaning of this is very, very simple. This is non-preemptive scheduling algorithm. I'm not saying P1 is scheduled and in between P2, then P3, again P1. No. Once process is scheduled for execution, until that process finishes, no other process will be scheduled. And that we already studied, the preemptive and non-preemptive, 2 versions of scheduling algorithms. Okay. So like whenever we see later on round robin, that is necessarily preemptive because a fixed time slice or time quantum is assigned. After that, we need to switch to next process. Now that won't happen in first come, first serve. Here, once process is scheduled, it will execute till its end. Once that process is finished, fine, then another process will be selected for execution. Of course, here we are not considering any blocking kind of a thing, like process is blocked for say some sort of input output. That part we are actually not considering. We are just considering CPU bus time here and not for IO bus time here. Okay. Now the execution of this is typically shown by this Gantt chart. Now this is most important thing that is required for all scheduling algorithms. Given the criteria, given the information about different processes, you should be able to draw the Gantt chart of schedule. Okay, so it's like a timetable. It's like timetable, right? Where on x-axis we have a time, and on y-axis usually we have processors, and that will be useful when we have a multiple cores. Right now here imagine like only one processor is there, and there are three processes P1, P2, P3. They arrived in the order, first upon P1, after that P2, after that P3. Then this is the Gantt chart. Now, in order to draw the Gantt chart, it is a very simple thing. Let me share a whiteboard kind of a thing. Fine. And now it is something like this. On this x-axis, we have, for example, time. So let me put it here. Time, okay, and maybe this is, or maybe after this, let me view. This is time 0. Oh, it is taking too much. Okay, fine. Let me draw. Okay, so this is time 0, and something like this. This is time 0. Right. Now P1 arrived first, and the burst time for P1 I mentioned here in the example is 24. So definitely what will happen is from 0 to 24, somewhere here, 0 to 24, something like this. Which process will execute is P1. This is execution for process P1, and this is the time 24. After this, once this P1 is finished, maybe after 3 time unit, and next process is there, and that is P2, because P2's burst time is 3, right? So 24 plus 3. Once P2 is also finished, then it is turn of P3, right? So here I can say this will be the P3, something like this. So definitely it will be from 27 to 30, something like this. So from 0 to 24, P1 will execute, 24 to 27, P2 will be executing, and 27 to 30, P3 will be executing. This is typically called as a Gantt chart. Now, if you consider all three processes arrived at exactly say time 0, they arrive exactly time 0, but the order is P1, P2, P3, then what P2 is doing from 0 to 24. That means what process P2 is doing when P1 is being executed. Very simple thing, during that time it is just waiting there. So P2 will wait while P1 is executing. P3 will also wait while P1 is executing as well as while P2 is executing. So we need to calculate now waiting time. Now from 0 to 24, P1 is executing. P1 arrives at 0. So waiting time is very simple. When that process is scheduled, what is the time? Minus when that process arrives. Now I said, assume that all arrived at time 0. Then, because P1 is immediately scheduled, waiting time for P1 is 0. Right? For process 2, that is for P2, okay, it started its execution at time unit 24. That means 0 to 24 it is waiting. So waiting time of P2 is 24. Similarly, for the process P3, P3 process is waiting when P1 was executing and P2 was executing. Actually, it started its execution at 27, right? So 0 to 27, actually it was waiting. So 27, it was the waiting time for process P3. So P1, waiting time is 0, P2, waiting time is 24, and P3, waiting time is equal to 27. Right? Now, that is the individual waiting time for each and every process. In order to check whether this algorithm is good or bad in terms of whatever the criteria we mentioned. So one of the criteria was waiting time, and that should be minimum. But anyways, whenever there are multiple processes, we should be able to calculate the average waiting time, not just waiting time for any single process. So averaging is now very simple, like 3 processes are there and waiting time of all 3 is 0 plus 24 plus 27. So we need to do the addition of these. So 24 plus 27, it is 51, divided by 3. Divided by 3 by? Divided by number of processes. Okay. So the formula is very simple. It is summation of waiting time for all Pi divided by number of processes. If waiting time is denoted by W, for example, if waiting time is denoted by W, or rather I can say Wi, something like this, Wi, where W denotes waiting time and I denotes ith process. Now here process number we started with 1. Okay, then the formula becomes very simple. It is something like, let me try to write it here. It is, or let me go to the whiteboard. It is something like this: summation of Wi, where I is equal to 1 to n, I is equal to 1 to n, divided by this summation, divided by n. So this is the formula. It's a very simple thing, right? Where Wi denotes waiting time of I process. Assume there are n processes. So I runs from 1 to n. So for example, in previous case, we have P1, P2, P3. Okay. So we need W1, W2, W3. So waiting time of process P1, waiting time of process P2, waiting time of process P3, divide by n. So here number of processes is equal to 3. Got it? So that is very, very simple formula. Now the question is, if we have another order of arriving process, does it do something better than this? That is the question. Okay. If waiting time, that is average waiting time, is calculated something like this, then my question is, for example, if we change the order, now actually according to this scheduling algorithm, we cannot change the order because whichever process arrives first will be scheduled first. That is as simple as like that, right? But then the question is, if they have arrived in some other order, what is effect on the average waiting time, right? So for example, suppose they arrive in this order, maybe at again time 0, but order of arriving the process is something like, first of all P2 arrived, then P3 arrived, and then P1 arrived, right? Now talking in terms of throughput, both are same actually. At time 0 we started, and at time minute 30 all three processes finished, right? So throughput is exactly same. So here again, they will start at 0 and they will finish at 30. No problem, no issues. It's perfectly okay. Okay. But now with this order of arriving the process like P2, P3, and then P1, P2 will be selected first. That is what algorithm says. Then P3 and then P1. That is the order. P2, P3, P1. So I don't think there is any doubt in case of Gantt chart, right? But then the question is, what about the waiting time? So waiting time for P1, now we need to see. See, P1 is scheduled at time unit 6 and it arrived at 0. So 6 minus 0, it gives me 6. One most important thing, because for simplicity, I assume here all three processes arrived at time 0. Okay, and that is the reason. So maybe this at time 6 it is scheduled. You may think 6 is the waiting time. No. For example, if P1 arrives at time unit say 2 and it starts its scheduling at 6, what is waiting time? So it is waiting for 2 to 6. No, so that is 4. That means whenever it is scheduled minus when it has arrived. And that is the reason I am repeating it here. 6 minus 0. I'm not just saying 6. Okay. So waiting time for P1 is 6. Waiting time for P2 is 0 because that is initially scheduled. So it is 0. Absolutely no issue. And waiting time for P2 is just 3. P3. Waiting time for P3 is just 3. Why? Because while P2 is executing, P3 is waiting. So P3 actually scheduled at this time, 3, here. Right? So waiting time of P3 is equal to 3. Now if you see the average waiting time, it is 6 for P1 plus 0 for P2 plus 3 for P3. That gives me 6 plus 0 plus 3, 9 divided by 3 is equal to 3. This is the average waiting time. Now in the previous example, if you see, average waiting time was 17 time units. 17 versus 3. This is definitely better than the previous case, right? But first come, first serve scheduling algorithms do not have liberty to change the order. Okay? The order in which process arrives should be the order in which process is scheduled. That is what the algorithm suggests. Okay? And actually, this effect is called as convoy effect. Which effect? Where short processes, in previous example, the P2 and P3, they are short processes. Just 3 time units are required for P2, 3 time units are required for P3. These short processes are actually behind long one, like P1 is long process, which needs 24 time units. Definitely they suffer. And this effect is called as convoy effect. Right? Any doubt in this? Any doubt in this? Yes. If you have any doubt in calculation, or because there are so many examples on this now. Okay, and not necessarily every time there is a zero arrival time. With different arrival time and different CPU bursts, given the algorithm, you are supposed to calculate average waiting time. Once you understand the concept of Gantt chart, how it is used to represent the execution schedule of the processes, then it is like a pictorial representation of schedule, right? So, do you have any doubt on this, on Gantt chart, on calculation of average waiting time? Because now I don't explain the same part again for next algorithm. Now there we'll just try to see the difference between different algorithms. Yes, please put if you have any doubt in chat box. Otherwise, we'll go with next algorithm.
Sir, chat box is not available.
It's not available. Let me check. Let me check. Now check. Is it available now?
Yes.
Okay. Fine. Now I'm getting response. Okay. So is it okay? Should we go with next algorithm? Right. Now from previous algorithm, we got one hint. Kshitij Sangor, so can you please summarize this part in short with highlights? What to summarize? The complete algorithm? Convoy effect. Okay. You want what is the convoy effect? Fine. Now it is very simple. It is very simple. So for example, whatever the two examples we saw actually, let me go to whiteboard. Let me check if I can erase everything. what we'll do is we'll try to see the convoy effect. Actually, the same thing we discussed. That is, say for example, this is my timeline. Okay, this is my timeline, and there are three processes: P1, P2, P3. Let me take the same example. P1 is with 24 time units, P2 and P3 with 3, something like that. And let me use two different colors or two different schedules. So first one, let me take the red one, where at time 0, P1 is scheduled. Then because that is scheduled, it will go up to 24 time units. Okay. And then next 3 units will be P2, and next 3 units will be P3. Right. Let me put that part in text box. So something like here it will be process 1, then here it will be process 2, and then here it will be process 3. Now, what is happening here? What is convoy effect? The short processes like P2 and P3 just needs 3 time units, right? But because they arrive after P1, their waiting time is more. Now let me select another color, another schedule. Let me select, say for example, green, where at time 0, sorry, I forget to put this time. So let me use like this one is 0, this one is 24, this one is 27, and this one is 30. That is what the first schedule is. Now, if we don't want convoy effect, that means the short processes will appear before long processes. Okay. So what will happen? Let me select another color and assume at time 0. Let me again select something like this. At time 0, P2 is selected, then P3 is selected, and then P1 is selected. So what will happen is, first of all, P2 is selected because this is short process. Then P3 is selected. This is also short. And then P1. Actually, on throughput, there is no effect at all. On throughput, there is no effect because in either case, P1, P2, P3 or P2, P3, P1, in both the schedules, total time required is 30. But now if you see the average waiting time, in first case, P2 is waiting for 24 units, P3 is waiting for 27 units, P1 is waiting just for 0. That means it is not waiting at all. So 24 plus 27 divided by 3, that gives me 17. Whereas if P2, P3, P1 is selected, P1's waiting time is 6, that is the highest one, just 6. P3 is just 3, 6 plus 3, 9. P2 is not waiting at all. So 9 divided by 3, that gives me 3. So that is effect on average waiting time, right? And considering this fact, where we want to take the smaller processes first, another algorithm is suggested, and that algorithm is, it is just because of that convoy effect, right? Another algorithm is shortest job first. Now see the name, shortest job. How we can say job is short? It is basically depending on the CPU first. Okay. So like in previous algorithm, what we have considered is the arrival time, whereas in shortest job first, what we consider is the CPU bus time. So associated with each and every process, we have now again the next CPU bus. Now this part is important. We need to understand this now. Next CPU bus. Why we are saying next CPU bus? Because as I already mentioned in yesterday's session that the overall structure of process is CPU bus, IO bus, CPU bus, IO bus, CPU bus, IO bus, something like this. Okay, so it is a mixture. So whenever already I executed one CPU bus, maybe there is IO bus and whatever the next CPU bus, because while scheduling we need to select the CPU bus depending upon CPU bus. So we need to do some sort of approximation on calculating the next CPU bus. Otherwise, anyways, that is required for a slight variation of this SJF, that is SRTF, that we'll see. So here we use these lengths to schedule the process with the shortest time. So the process which needs the shortest time of CPU will be scheduled. That is what the shortest job first. Okay. For example, you can imagine something like you are at a grocery shop, okay, and say two persons are there. One is with say 50-60 list of grocery items. So okay, he has lots of grocery items to buy, and the list is there in his hand. And another person who just needs say one of the item. Okay, say any one item is there. Single item is expected. Now what the grocery shop does is he actually looks at both, and even though the person who actually come earlier than other one, okay, he frees that person first who just needs single. Why? Otherwise, that person has to wait for the total time for another person who have the list of say 50-60 items of grocery. So who needs the shortest time will be freed first, something like that. Okay. But anyway, if it is something like one needs 50 items and one needs 45 items, then no, grocery shop don't go with 45 because whoever comes first, so maybe he is applying the FCFS algorithm. But when the time difference is really high, in that case, like for example, shortage job for scheduling can be selected, where scheduling depends on not arrival time but on the next CPU burst. Now, definitely because shortest jobs are selected first, this SJF algorithm is optimal. Optimal in terms of average waiting time. This always gives you the minimum average waiting time. But then the problem is how you know that like of next CPU burst. This is difficult. So this is theoretically, even though we are saying SJF is optimal, it is really hard to find out what is the length of next CPU burst. Okay. Or maybe we could ask the user. So theoretically, if like P1, P2, P3 is given and whatever the CPU burst time is given to you, then it is really simple for implementing it. Because if you imagine given your program also, you imagine something like I think I given yesterday example of finding out the prime number. Okay, if n is really high, How much time is required? Really, we don't know. Maybe that number is divisible by 2. So with very first division, with just single operation, you conclude number is non-prime. And if it is really huge prime number, you need to divide up to square root of that number. And in that case, the CPU bus times, how to decide that? So that is practical difficulty in knowing the length of next CPU burst. Okay. So this is a shortest job first scheduling. Now let us see the example. Now there is some mismatch actually. So this is the burst time shifted here. Okay, and these are the processes. So in this example, there are 4 processes: P1, P2, P3, P4. P1's burst time is 6, P2's burst time is 8, P3's burst time is 7, and P4's burst time is 3. Now, irrespective of their arrival time, if I assume all are arrived at 0, no problem, because anyways we are not going to see that. Now, as I am saying, it is shortest job first. I just look at this column, burst time. Which one is the shortest? Yes, 3 is the shortest. Because 3 is the shortest, P4 is selected first. This is done. So P4 is selected first. Now out of remaining, now burst time of this is 3, no? So it will start with 0 and it will run up to 3. So 0 to 3, P4 is selected. At time 3, yes, P4 is finished. Now when scheduler is activated here, because now P4 is finished. Remember again here, what I am saying is when P4 is finished, that means this is non-preemptive. That means it is non-preemptive algorithm. Now, 3 processes are there, P1, P2, P3, P6, 8, 7. Now, which one is selected? Out of these 3, this one is selected, 6. So, P1 is selected here. So, from 3 and these 6 units, 9. Up to 9, it will be executed. At time 9, this process is also finished. So at time 9, 2 processes are there, P2 and P3, with 8 and 7. 7 is the lowest one, so 7 will be selected, which is P3. So P3 is selected. So 9 plus 7 plus 16, it will run. At time unit 16, what happens is P3 is finished. At time 16, scheduler finds that there is only one process, that will be selected. And it needs 8, so 16 plus 8, 24. At time 24, it will be finished. So the sequence of execution is P4, then P1, then P3, then P. And because all arrived at the same time, that is time 0, P4's waiting time is 0, P1's waiting time is 3. So this is P4's 0. Please explain average waiting time for this exam. Yes, I am explaining that only. So see here, P4. P4 is scheduled first, no? So P4's waiting time is 0. It is scheduled at time 0. So this is for P1. This is for P2. This is for P3, and this is for P4. So P4's waiting time is 0. So that 0 is selected. P1 is scheduled at 3. So P1's waiting time is 3. So 3 minus 0 is 3. Next, P3. P3 is scheduled at 9. So 9 minus 0 gives me 9. What I am subtracting minus 0, when I say minus 0, that is the arrival time. Huh? Don't get confused there. You may wonder why I am subtracting 0 when there is no effect. If the arrival time is different, there is definitely effect on that. Okay. Next, P2, it started scheduled at 16. So 16 minus 0 gives me 16. Now 3 plus 16 plus 9 plus 0. So 16 plus 9 gives me 25 plus 3. 28 plus 0 is 28 divided by 4 is equal to 7. So that is the average waiting time. Something is there on chart? With SJF approach, how long does the largest job has to wait? Means what? They will definitely CPU can't put a job hold forever. So that is threshold value for that. Okay. Okay. This is really very good question. For example, what will happen to the longest job? Even this is the single snapshot. You imagine something like before it's finished, P1 is finished, and another job that arrives with say P5 with time unit 5. That will be selected. If that is finished, say another one is arrived before finishing that with time unit or bus time 3. That will be selected. That means P3 is waiting, P2 is waiting. Okay. If new jobs are coming and coming and coming, they are just entering into the system, whose CPU bus time is less than say P3 or P2, right? What will happen? How long P2 and P3 will wait? This effect is called as starvation. This effect is called as starvation. And of course, there are solutions for that. There is something called as the aging policy. Of course, we will see that later because anyways that we need to discuss. But remember, yes, like previously, the shortest job behind longest are suffering with waiting time. Here, longest job will suffer. Even though this algorithm giving optimal value for average waiting time. And definitely we need to have some sort of solution for that. Aging policy we need to add there. Aging. Anyway, that we'll see later on because first of all, let us complete this one. SJF. As I already mentioned, SJF gives the minimum average waiting time. First of all, previous question was explain average waiting time. Is there any doubt on calculation of average waiting time? Calculating average waiting time is very, very simple. Okay. Now, no, actually, ready-made thing is given here. Ready-made thing is given here, but anywhere, P1, P2, P3, P4 with 6, 8, 7, 3, if that is given, you can directly draw a Gantt chart. So you draw a line. First of all, P3 is selected, whose bus time is 3. So 0 to 3, sorry, P4, not P3. So 0 to 3 will be P4, something like that. Okay. Okay. So that is. Now we'll discuss upon how to determine length of next CPU bus. This is one of the possible solutions they have mentioned, for which it is just kind of an approximation or you can say estimation. Okay, so this is the estimation of next CPU bus considering the previous one. There is a small assumption which is not necessarily true. Most of the time it is true, but maybe some exceptional cases also there, right? But the thing is how to determine the length of next CPU bus, and for which this is the estimate given. And this estimate is basically based on length of previous burst. Okay. So first of all, we estimate the length and then we apply the algorithm SJF here, where we pick the process with shortest next CPU burst. And this is calculated using these steps, and these steps are actually called as calculating the exponential average. Some sort of, rather I can say it is kind of a running average. The same thing what we do with integrations. In mathematics, integration is used for that purpose. Okay. Now, how to do that is, for example, four steps they have mentioned, where T of n is actual length of n CPU bus. Now, because we want to calculate the next CPU bus, assume there is one process, say P1, where 5 different CPU buses are there. Now, P1, for a process P1, first burst is denoted by, say, for example, T1. T1, T2, T3, T4. Say, 4 CPU bursts are there. Now, actual length is known for the CPU burst which has already happened. Like first burst is already happened. Now we know that length. So that means previous knowledge we have with us. So this is the actual length, and depending upon this actual length, we want to calculate this predicted length. Remember here I am saying n plus 1. T of n plus 1. Actually this is T and this is 2. So this is the predicted value. So for n plus 1 CPU bus. So plus 1, that is used to mathematically denote the next CPU bus. Okay. And some alpha is taken there, and this alpha is actually the probability of the calculating running average, exponential average. This is between 0 to 1. If I put the value of alpha is equal to 0, that means I am not considering at all the previous or historic data. If I say alpha is equal to 1, that means I just want to think like the next burst is equal to the previous. And this is the formula to calculate the next burst, something like this. Okay. So try to understand it here. Here it is wrong. It should be n plus 1. T of n plus 1 is equal to, now alpha Tn, we know that Tn is the actual length of n CPU bus, and alpha. So how much percent of previous? Now, if you see the next bullet, we say it is equal to 1 by 2. 1 by 2 is nothing but what? 50%. So we want to calculate average based on something like 50%. Fine. So what we are doing is to take the exponential averaging like alpha Tn plus now 1 minus alpha. Now anyways, if I take it as a 50%, then it is fine. If it is 50%, then 1 minus alpha is also 50%. Got it? So this is actual one, this is calculated one. Right? Predicted value and actual value. Actual values are only available for previous CPU bus. Right? So that is how to calculate next CPU bus. This is the formula rather I can say. As I already mentioned, SJF is non-preemptive. We can implement preemptive version also. Preemptive version of shortest job is also possible, wherein rather than activating the scheduler when previous process is finished, what we'll do is we can activate this scheduler whenever new processes arrive also. So for example, P1, P2, P3, P4, four processes are there, right? And now, say for example, P4 is executing because its CPU burst is less. Maybe another process arrives with lesser CPU burst. So P4 has to be stopped and new process with less CPU burst will be selected. This variation, this variant of SJF is called as SRTM, shortest remaining time. And remember here, what we are saying is remaining time. Remaining time is what? If process is not at all selected for execution, remaining time is complete CPU burst. But if it is preempted, say for example, for one of the process, the CPU burst is say 8 units, it has already executed for 2 units, but in that case, what happens is here 6 is the remaining. Okay, so that is remaining time. Got it? So there are two variations of shortest job. First, one is preemptive and one is non-preemptive. The default version is non-preemptive, that is FJF, whereas SRTM, that is shortest remaining time first, it is the preemptive one. This is kind of exponential averaging. Okay. So Ti is actual, tau I is the guess, the predicted one. This is just one example on that of exponential averaging. Okay. Now let us see this example for shortest remaining time first. Actually, it should be next SRTM. It is called as SRTM, shortest remaining time next. Okay. Now, again, I think it is already 11. Okay, fine. So we will stop here. We'll continue with this example in next session. Okay.